You're watching Economics Amplified, the latest thinking on the biggest issues from UChicago's Becker-Friedman Institute.
Welcome to this this nice panel discussion which we have. My name is Lars Hansen. I'm the director of the Becker-Friedman Institute, and I want to be absolutely clear. This is in spite of my presence here, this is a student organized event. The Becker-Friedman Institute helps to secure funds and to encourage people to participate. But this is really something that's been organized by the graduates, by the undergraduates, and is their event. I'd like to take this opportunity to thank the CME Group Foundation for generously funding this event. Over the past few years, the foundation has supported the BFI and other undergraduate activities, and we think this has had a very important impact on young students in economics and finance and elsewhere. Previously, we've had sessions that featured regional Fed presidents, that featured chairmen of the Council of Economic Advisors and the like, and so we're anxious to kind of today push in this direction of related to big data. So this topic is very clearly at the forefront of businesses, governments, many fields of academic study, including economics, statistics, and computation. The student organizers have engaged 3 distinguished leaders with expertise in this field, and I'm certainly looking forward to hearing their discussions of the evolution of big data analysis. I'd like to acknowledge the many student volunteers who have participated in the planning of this event, and I'd like to introduce the 2 student moderators. Kyla Reinhertz is one, and the other is Justin Manley. They're both 4th-year students in the college, and they've both kind of led and put forth a great effort to bring this event to fruition. Kayla has served as president of the Chicago Society and also was a key presenter on the Federal Reserve Challenge team. Justin has been working on software development and data analysis for startups and nonprofits, and currently is involved in a very big data project for Argonne and for the Computational Institute. So without further delay, I'd like to turn things over to the 2 of them who will be running and moderating this exciting session. Thank you.
Thank you, Professor Hansen, for your introductory remarks. We're incredibly grateful to the Becker-Friedman Institute for all of its generous contributions to undergraduate economics. To name just a few, the Friedman Forums, the REU program, and the yearly undergraduate organized panel allow students to connect with family, faculty, learn new research tools, they're like family, and interact with world-renowned experts. There's so many people who helped us prepare for this event that I'd like to acknowledge. I want to thank Professors Amit Bashandari, Michelangelo D'Agostino, John Lafferty, Victor Lima, and Grace Young, the undergraduate big data team, and the entire team at the Becker-Friedman Institute.
My name's Justin Manley, and I'll be moderating today's discussion along with Kayla. I'm now excited to announce our distinguished panelists. Susan Athey is the Economics of Technology professor at Stanford Graduate School of Business. Since 2007, she's also served as a long-term consultant for Microsoft, including a tenure as chief economist. Athey is also the recipient of the 2007 John Bates Clark Medal and the Elaine Bennett Research Award. Welcome, and thank you for being here.
Many of you will recognize our next guest, Hal Varian, as the author of our intermediate micro textbook. Hal Varian is the chief economist at Google. He started in May 2002 as a consultant and has been involved in many aspects of the company, including auction design, econometrics, finance, corporate strategy, and public policy. He is also an emeritus professor at the University of California, Berkeley in 3 departments: business, economics, and information management. Welcome, Professor Varian. Larry Wasserman is a professor in the Department of Statistics and in the Machine Learning Department at Carnegie Mellon University. His research is on high-dimensional inference, topological inference, machine learning, theoretical statistics, and astrostatistics. He is a fellow of the American Statistical Association, a fellow of the Institute of Mathematical Sciences, and is a recipient of the Committee of Presidents of Statistical Societies President's Award. He also worked briefly in Kazakhstan as an animal trainer. So welcome, Professor Wasserman.
On behalf of all the students, Kayla and I are delighted to welcome you here this afternoon to the University of Chicago. Thank you for being here. And thank you guys for joining the discussion. We're going to begin with opening statements from each of the panelists. We'll move into a moderated discussion. And then we'll conclude with questions from the audience. Professor Athey, would you like to start us off?
So thank you so much for including me in this discussion today, and it's really a great pleasure to be here. And actually I want to just mention how important I think it is for organizations to be doing events like this for undergraduates, because I think personally this moment in time is the most exciting moment I've seen in my career in economics. There's a few sort of old fogies like me and Hal who are out there taking advantage of this transformation that's happening to social sciences and economics. But you all are the ones who are really going to be a part of how big data changes science as well as business. Whatever path you follow, you're the ones who are going to really take these ideas that we talk about today forward. And so I really like to talk to young people, because actually you're at the moment now where you can make decisions that will allow you to best capitalize on some of these really exciting things that are happening. So you all need to, at the end of this, I hope you're going to go back, if you have not taken a good programming course, and if you have not taken a machine learning course before you finish the University of Chicago, you've just screwed up the rest of your career. So I think you should, everyone in here should go and do that. Okay, so let me make a few comments, and I want to say I really have sort of three lenses when I sort of talk about this topic. There's sort of the science and practice of doing big data, which itself can be divided into sort of methodology as well as applications. Then there's sort of what does management and organization and business do differently in the face of big data? And finally, what are the implications for industries and economies? So in my remarks now, I'm going to focus mostly on the first one, because that lends itself best to a sort of formal presentation. And hopefully in the panel discussion, we'll bring out some of the themes from the second too. So, how many of the undergraduates here have taken econometrics already? Excellent. So you're gonna, you've learned a lot about how to use data to ask questions. And so probably, how many of you have taken a machine learning course? Only a few. All right, now you're all going to sign up for one next year. But so what I'm going to sort of speak to the audience of social scientists who have a traditional toolkit and try to tell you a little bit about what I've learned from spending a few years being the only economist in a sea of machine learning people, about what I learned from them and what I think they can learn from us. So first of all, just when we think about when I started working with Microsoft, they have I worked with their business, and they have a research organization. And so a great thing about working with them was that I could, from the very beginning, be doing academic publishable research using all of their mountains of data. And so, but I quickly figured out that I was totally unprepared for this. So I basically had to get like another PhD to be able to operate in this environment. So what were all the things I had to learn? Just actually getting data, extracting it and manipulating it requires a whole set of tools that I wasn't trained for. We have to do lots of things. I'm doing work with the news media. So we have a project. We look at internet browsing data, and then we scrape the articles, and we crawl web pages, and we understand where news was presented and how it was organized. And then we use classification algorithms to put it into categories. And then we use crowdsourcing. So we have workers on Mechanical Turk code it and so on. And then we try to generalize from that using various methods. None of this was anything I knew how to do. But it allowed me to do research that I never could have done before. And then when I go to analyze the data, I also didn't know how to do efficient computation on large scale. If I had terabytes, petabytes of data and thousands of machines to help me do my analysis, how did I actually change what I did to make that work? So lots and lots of things to learn, and when you're young, this is your chance to learn it, and so it's not intimidating. I was already tenured, I already had all these prizes, so I could say, all right, I'm gonna spend 3 years and learn all this stuff, but it's a little harder when you're young to make those investments, but when you're in school, you get the chance. So I've got now I'm going to sort of summarize in sort of one slide sort of the methodological stuff that I think I learned from some of this experience. So first of all, supervised machine learning is sort of one part of machine learning. And this is a set of tools that are really well developed and widely used in certain disciplines. And I would say it's rapidly growing in influence. So I think like 1,000 undergraduates took the machine learning course at Stanford this year. And so what are these methods? Well, the supervised machine learning, they're particularly good at cases where you have a lot of data, but you also have a lot of descriptors. So if I have an individual who's going to, and I have seen all of their web browsing history, I could think about having an infinite number of ways to describe their characteristics. So machine learning is going to be really good at trying to find the best model, how to find which of those variables are important, and how I should define and how I should build my statistical model to do prediction. They also really emphasize data-driven techniques for selecting your models. So they focus a lot on predictions and applications of predictions. One of the big weaknesses, though, is that they don't focus a lot on causality. And so causality is really like the science of, well, what if questions. And of course, everything we do in economics and a lot of the rest of social science is thinking about causality. What would happen if I changed the price? What would happen if I shut down this marketing campaign? What would happen if we changed the minimum wage laws? Okay, so that's the whole focus of social science and economics. That is not the focus of machine learning. So, econometrics, social science, and statistics have really well, that's the main thing we've thought about, is how do we answer those kinds of questions, but usually in small data sets. And we have kind of two kind of distinct lines that do that. One is sort of thinking about treatment effects, and that thinks about more simple models, and then some models are more complicated, like models of people's behavior in auctions or firm pricing decisions. So, these are really well developed and also widely used. They're used, the Department of Justice and, businesses that set prices use these kinds of models very widely. But the thing that goes wrong with these is that we really don't know how to apply these techniques very well to big data sets. And some of the particular things that go wrong is, if I have 3 variables, I can think really hard about how to specify my model. But if I've got thousands, nobody has a theory of how 1,000 variables, affect your outcome. And so you really need things to be more principled and model driven. And so what I think that where I'm trying to do research to bring these things together is to combine the best of both worlds. I want to be more systematic, I want to be data driven, and I don't want to pretend I have a theory when I don't have a theory. But at the same time, my goal is to answer what if questions, to answer causal questions, and I want my methods to be tailored for that. So, I won't go through sort of the specific papers that I'm working on. I'd say there's a video of one of the talks I gave at the National Academy of Sciences 2 weeks ago that goes into a lot more detail on this. But basically, one of the research agenda, or one part of the research agenda, is to bring together these big data tools and apply them for causal inference. And it turns out that if you're asking these kinds of questions, you need to use the tools in different ways. Let me mention another thing that actually was completely new to me. I never even thought about this way, which is unsupervised machine learning. So you might sometimes read in the newspaper, oh gosh, these amazing scientists discovered cats on YouTube. What the heck does that even mean? I couldn't even translate that into a scientific statement. Well, it turns out that this is an application of unsupervised learning, which is trying to find patterns in data. It's not like I have a bunch of X's and I'm trying to predict Y, but I'm trying to find similar things. So just as an application where I use this in my own work, when I was studying news, I looked out and saw all the news people read, and then I looked at the articles and the text of those articles, and I was asking questions about how Google News and Facebook and Twitter affect the kinds of news that you read. So as an input into that, I took all of this text and I tried a bunch of different methods. This particular method worked really well. I constructed a network among all of the articles, and a link between the articles was formed if they had words in common, and the strength of the link was determined by how many words they have in common. And so I didn't discover cats on YouTube, I discovered President Obama's prom night. Okay, so there was a bunch of articles, I never would have thought to look for that in the data, but there was a bunch of articles that had sipped champagne, fun and happy, and prom night in this particular week, and it turned out it was a set of articles about President Obama's prom night. So that what the algorithm found was the cluster of similar things, and then I just look at it and give it a name. But of course, if I have lots of them, I don't have to name all of them, it's just finding similar things. And so actually what I did with this is I tried to figure out which of these were political and which weren't political. And then I could focus in my scarce human coding on the ones that were political because I was interested in studying political bias. And I might ask different kinds of questions for ones that were about different topics. Okay? So just as an example, for a couple of weeks in 2013, these were the topics that my algorithm discovered, and as you can see, some of them are have quite potential for political bias and others don't. So this was a nice little machine learning technique that I could use in order to use as an input for the statistical analysis that I did, which used more standard techniques. So just to kind of then give a little bit of a taste of some of the different kinds of economic research you can do. There's so many new data sources, and I've just kind of put up like a whole range of them. I just want to emphasize that every single field of economics is going to be impacted, from public finance, labor economics, political economics. Everything is going to have new possibilities, and that is so great for young students because you know what? 50,000 people have analyzed the public census data before. But you might be the very first person to analyze a new data set, and that gives you a much greater chance of discovering something new. Basically, the first mean you run is a discovery, and that's one of the things that has just, I'm so excited to get out of bed in the morning. Like every day, I'm discovering something that nobody knew before. And what could be more fun than that? So just a few of the things from my own research that I've found in a lot of different areas. As I mentioned, we've been studying news. Another set of papers looks at how people learn about financial information. And so I looked at how individual investors find information on the internet and then found that that's predictive of anomalies in stock prices, and it can help us understand why stocks move in certain ways at certain times when I can link that to how people they read news or what they did prior to doing internet research. Another line has looked at advertiser behavior, and so this fits into behavioral economics. One thing that's been really hard over time is for us to use empirical models of people's irrationality. But if I'm watching advertisers and I see the same advertisers like over a year, and I know that they're getting shocks that are done by the system basically every week or every other week because they keep changing the back-end algorithms, and if I know about that, I can actually really understand what people's preferences are. And so I can identify structurally what their preferences are, and I can say, well, this set of people really looks like they're just trying to advertise so they get to the top position on the page. And this set of people is trying to maximize profits from clicks. And this guy's behavior cannot be rationalized by any profit maximizing model whatsoever. That is a really, it's the same kind of things we've done before, but with this type of data, I don't have to assume everybody's rational and has the same objective function. The data can tell me what their preferences are, and that's really fun. One of the last things I've been working on is the Bitcoin network. So that's a huge network of transactions. And so I've been both analyzing people's behavior on it, as well we did a large-scale experiment at MIT where we gave $100 in Bitcoins to all the undergraduates, and we're able to then see how they use them. So just to kind of sum up, I think there's this is a moment in time where social science and economics can do so many things we couldn't do before, but we have a heck of a lot to learn if we're going to do it well. We need to learn from other disciplines, not be too conceited that we know everything, but actually realize we have things to learn, but also hang on to the parts that we do really well. And so this has parallels. Hopefully we'll come back in the discussion in business as well, because business also is undergoing a scientific transformation. How decisions get made. It's more data driven, it's using more experimentation, it's using more machine learning, more big data. And so just like science is going through a transformation, so is the business world, and that's going to have implications for our economies. Thanks very much.
I think I should start with some apologies. I usually end with them, but I have a cold, and so my voice is very hoarse. And so if you can't hear me, just let me know, and I'll try to drink some water and speak louder. And my second apology is I'm not an economist. I'm an outlier here.
He's the one we need to learn from.
Well, that's a very kind way to put it. And third, I'm very underdressed. and I'm sure I'll think of many more things to apologize for later on. All right, so the title of this thing is How Big Data is Changing Economies. I almost didn't come because I don't know anything about that. And I think it was Kayla who I wrote to, perhaps, and she said, no, we really want you to come anyway, and plus you get a free dinner. So I decided I would come. So what does an academic do when you don't know how to answer the question? You change the question. How do you advance this?
That one was for Guinness.
So I'm going to change the topic a little bit. By the way, the other thing was I prepared 67 slides, but I promise I won't go through them all. So I'd rather, what I can talk about is what I know about, which is a big data, a statistician's perspective, and which I can summarize this way, which is big data plus bad analysis equals bad decisions, which is sort of obvious, I guess, but yet I think the point is very important. So who am I, first of all? I'm a professor of statistics at Carnegie Mellon. My main appointment's in the Department of Statistics, but I have a joint appointment in machine learning. So I've been very fortunate because we have a department of machine learning at Carnegie Mellon, and they're very welcoming to the statisticians. So I've been part of the whole growth of, and seen the whole growth of machine learning, and it's been very, very exciting for me as a researcher. And, but I've also been able to step back and see it as a statistician and how it's taking place, both the excitement of it, which is undeniable, but also certain concerns. And my main points, in case I don't get through everything, which I won't, is statisticians, I think, and you'll hear this complaint from every statistician you talk to, is that, and we do complain a lot, statisticians, statisticians are being left out in a certain sense of the whole big data, data science world, and I'll tell you why I think that's so in a few minutes. But if that was the only message, you could say, well, that's too bad for you. I mean, you should do something about that. But I think it's worrying for everybody, because I think statisticians being left out of certain initiatives that I've seen means that some things are not being done very well. Now, all of you actually, in a certain sense, are exceptions, because you're economists and you're one of the few fields where you do get training in statistics, right? So I noticed Susan didn't say you should also take a course in statistics, but that's probably because you all do take a course in statistics. But it's not true, for there's a lot of people out there doing big data and machine learning who really don't learn basic statistics. And I think this is kind of a tragedy. And also something I'm sure I won't get time to talk about is big data, and I've found this in my own work, can lead you to want to fit very complex models, because you can ask much more subtle, nuanced questions. This happens, I work with astronomers, and this is what happens. We have data sets from satellites and telescopes that are huge, but the questions get very complex, and all of a sudden, the amount of data points per parameter can get very small, even though the data set's big. And so everything you learned in your statistics class is still important, even with big data. And then I'll talk about the future. Okay, so where are the statisticians? So I'm just picking out a few random facts here. The President's Council of Advisors on Science and Technology, 0 statisticians. The United States Office of Science and Technology named a chief data scientist, very smart person, but I happen to notice he's not a statistician. Forbes listed their world's 7 most powerful data scientists, 0 statisticians.
Is Hal on the list?
I don't remember.
Well, it's clearly a lame list.
Yeah, it's a bad list. It's a bad list. And I can go on and on about things I've seen at my own university, various initiatives that get started from different directions. And no one thinks to call statistics. They get CS involved, they get all these other departments involved, and they always leave out statisticians. And so this worries me as a statistician. But more important, I want to tell you, why should you care about this? Why does it matter to non-statisticians? And it's for the obvious reasons. As I said before, it doesn't matter how much data you have. And I think this is, relates to a lot of what Susan said, which is that you have to still do good analysis to get good answers out. There's a quote I like from Gary King from Harvard. It says, big data is not about the data, it's about the analytics. It's just as important. This is an unfair statistic. This is an example of bad big data analysis. I went to Google and I just searched big data, bad analytics. Got 10,700,000 hits. That's highly unfair, but it is interesting to do this search and look through a few of them, and you'll see some horror stories there. So they're not all 10 million are real examples of this. And after all, statisticians, I would argue, have been doing data science for at least 100 years. And the analogy I like, so I teach in machine learning and statistics, and when I teach the statistical machine learning class every spring, it's full of computer scientists, statisticians, engineers, not that many economists actually. And I try to explain to them that how important this is, and I always use the same analogy, which is you need brain surgery, and you go into the operating room and the world's best cardiologist is there. I don't care how smart that cardiologist is there, you want a brain surgeon, right? So you want brain surgery, you don't want it done by a good cardiologist, you want data analysis done. I think you want a statistician involved at some point, at least. All right, so big data in the economy. This is the 4 questions. This is not Passover anymore. Maybe it is actually, some of you know what I'm talking about. But there's 4 questions we're going to talk about. I think I'm going to skip this since I have like 3 minutes left. These were my answers to the questions, but we'll get to them. I think I'll just get to them during the discussion. That's probably a better idea. So the statistical issues that persist even with big data are sampling bias. That's still going to happen. Correlation is not causation. No, it's an oldie but a goodie. And it's just as true with infinite amount of data. You all learned in your econometrics class, if you've taken it, that identifiability has nothing to do with sample size. The effects of mining the data, looking for things, seek and ye shall find, multiplicities, things that we teach people how to deal with in statistics and in econometrics that are often overlooked. And more generally, just the whole notion of rigor. What assumptions are you actually making when you do this? And what is the best you can do under these assumptions? And I find that's something that's often missing in a lot of the machine learning literature. Why are statisticians left out? I'll just spend 30 seconds on this. It's mostly our fault. We're conservative by nature. After all, we're trained to reject null hypotheses. And very stubborn. Every statistician I met is very stubborn. Very inflexible. I think it attracts people like that to the field. Very bad at selling themselves. I can tell you from personal experience, when you go to a party, you don't say you're a statistician. That's why I put the thing about animal trainer into my Frankly, statisticians are afraid. I think a lot of statisticians are terrified of what's happening right now with big data. And really, we are experts at saying what you can't do. And I'm going to just tell you, I think this is where I'll finish, and I'll skip the rest of my talk. Because I want to tell you a true story. This is something that, and it's happened to me more than once, and I think it's really indicative of what happens. So I work a lot with these astronomers. And one day an astronomer came and asked us a very interesting question. And we spent several months learning the science because we felt that we shouldn't be trying to analyze the data without understanding the subject matter. And also cleaning the data and doing all kinds of stuff. We analyzed the data very carefully. After about a year, we produced some modest results. The data weren't that great, but they were, I'm actually melding a few stories together here, but I hope that's okay. But anyway, we had some results. What I didn't know, and what I found out later, was in the meantime, she went to one of my friends in ML. And believe me, I love my friends in ML. I work closely with my friends in machine learning. But they produced in 2 days very fancy plots, all kinds of very impressive analyses. And our first reaction was to complain, was say, yes, but what they did wasn't rigorous. They didn't write down their assumptions. They can't prove anything works. They don't really have models written down carefully. And we might be right at a certain level, but on the other hand, if I was the astronomer, who am I going to go to in the future? So I think this is something that statisticians need to think about, and maybe economists too, which is that, because I think economists are well trained about being careful about stating models and assumptions, but you also got to deliver. And I think this is something that's very important and certainly not part of statistical training. I can't really comment on economics. All right, so I'm just going to jump to the end now. I had a bunch of other stuff. There's even fractions in here and all kinds of stuff, but interaction terms, I'm sorry about that. Okay, I'm jumping ahead. So the last thing I want to say is conclusion. So first of all, despite sounding somewhat, saying some negative things, I agree with Susan. I wake up every morning. I think it's the most exciting time for so many different sciences, for statistics especially, for computer science, for economics, and it really is an amazing thing. Just to give you a sense of this, we used to have 4. I got a refresher time. I got extra time somehow.
They're counting up and not down.
Oh, I'm over by that much. All right. Okay, I get it. 1 minute. Very exciting time. Forgot my train of thought. So it's very exciting. Statisticians need to be very assertive. That's if any of you decide to become statisticians. Big data users, though, if you're not, if you're going to be doing big data stuff, think about including a statistician. We're pretty nice, actually. Come and talk to us. And a huge thing is funding. All of my friends in CS get oodles of money from the government, and we get these grants that are like a tiny fraction of those things. So the way I'm looking at this, and the main reason I'm here is, you're all University of Chicago undergraduates in economics. Some fraction of you are going to become very wealthy. So when you go to make a big donation when you're older, remember that statistics departments are very poor. And I'm totally serious about that. And the last point really though is I want to emphasize that big data and data science, it works best, of course, I'm talking about statisticians, but I think everybody understands. It works best, it's very interdisciplinary. Economists, computer scientists, statisticians, astronomers, whatever. It works best when everybody works in teams. Sorry for going over my last apology.
So, I thought I would do something unusual and give a talk without slides. And the question is, what should I talk about? So I thought about big data and economics, how it impacts our profession. I thought about big data and econometrics, how it impacts our methodology. Then I looked closely at the title, and it's actually about big data and the economy, or the economies. So it's more than just our profession. I think we want to think about how big data is impacting entire economies. And I was lucky that I already had talked about this. 5 years ago, I gave this Ely lecture at the American Economics Association on computer-mediated transactions. And this has been kind of an obsession of mine for many years. So I think I'll tell you a little bit about what that means and how it impacts the economy. Starts off with the observation that there's a computer in the middle of almost every economic transaction. Maybe it's a simple computer like a PC serving as a cash register, or maybe it's a data center. We've got some vast amount of processing capability, but most economic transactions now are computer mediated. And what does that imply about what you can do with all that computer-mediated capabilities? Well, one, you can do data extraction and analysis, and that's really the big data theme that I'm sure we're going to talk more about. But the second thing is you can do this personalization and customization where you can attune the transaction to the specific needs or interests of the parties involved. So it can be much more personalized and optimized for specific uses. So the famous example is, of course, Netflix that had this recommendation system for movies. And they found out that 75% of their views were coming from the recommendation system. So they said, how can we make this recommendation system better? Are we as good as it'll get? Or are there people out there that could improve on it? So they set up a prize, this Netflix prize of $1 million for anybody that could improve their system the most over a 10% improvement. Several groups around the world worked on this, and finally one group from Belcor actually won the prize. They managed to improve its performance by over 10%. The way they did it, interestingly enough, is they blended 800 different models together. And one of the nice insights was, they said, we found early on that it was much better to develop a new model than it was to try to improve one of the models we already had, which is kind of surprising from the viewpoint of how science is conducted, and I think particularly how economics is conducted, but I'll come back to that a little later in my remarks. Third thing that this computer-mediated transaction enables is continuous improvement. via experimentation. So back in the 70s, people were talking about the Japanese term for continuous improvement in production, Kaizen. Well, now we have computer Kaizen, because the computers can improve continuously, learning not just in a batch mode, but learning in real time to improve the nature of the transactions that they are mediating. So as an example of this, if you think about Google or Bing, search engines, we run over 10,000 experiments a year, roughly 5,000 in search side and 5,000 on the ad side. And these experiments deal with algorithmic improvements, or things that we hope will be algorithmic improvements, because you only know if they really improve something by going out and running the experiment. They also deal with user interface issues, with new products, and many, many different other capabilities. And we made these systems available not just to ourselves, but also to our advertisers. So for example, we have something called ACE, or Advertiser Campaign Experiments, where advertisers can specify different creatives, different biddings, different budgets, whatever they want, and then run an experiment to figure out which particular configuration is the best. And on the publisher side, it's the same thing, where a publisher can come up with several different choices for a web page, and the system will rotate among these choices and pick the most effective. And this latter one, it's kind of interesting, because you don't want to do the traditional A/B experiments that we usually look at in elementary statistics or economics, because that can be very wasteful. Doing these experiments are expensive, because you're spending a lot of time doing things that aren't fully optimal, because you're trying to see whether you can improve on things, and at least some of the things you're doing aren't as good as the best thing. So we do that one by using what's called a multi-arm bandit approach, where you're sequentially doing a kind of sequential testing. Great advantage is it throws away the losers very quickly, and you end up with just a horse race between the winners. And finally, the last thing, which is a little different than the other three, that's something I call contractual innovation. And that's really a profoundly economics concept, in my view. The idea is that you can contract on things that are observable. So I can say, I'll give you $2 and you give me a latte. And the expectation is that they'll get $2 of real money, and I'll get a good latte. There is a story about Abraham Lincoln, who was given a hot beverage. He took a sip. He said, "Madam, if this is coffee, please bring me tea. If this is tea, please bring me coffee." So in fact, you don't always fulfill the contract that you've made when you're ordering that $2 latte. But the nice thing is, when you have the computer in the middle of all these transactions, it can observe all sorts of things that were previously unobservable. So you can make contracts on things that weren't really feasible before, because you didn't have the data to really validate whether those contracts were effective. So think about today's poster child of .com is Uber, right? Everybody's very keen on Uber. The elevator speech in Silicon Valley now is, "I'm going to be the Uber of X." And then you just run through all the possible X's. But so the idea there is, it used to be a taxi cab transaction was just a one-time transaction. It was probably the only time you'd encounter the taxi driver, and the only time the taxi driver would encounter you. Maybe you're in a strange city. There was possibilities of opportunism and abuse of one sort or another. But now with Uber, you come to the transaction, you've got your whole history attached. Okay, you've got the whole history attached, and both parties are monitoring the performance of that transaction. Namely, what's the route that's being taken, how long did it take, what the fee is, and all of these other capabilities. Airbnb is the same way. 5 or 10 years ago, people would be very wary about renting a room in their house out to a stranger, but now they're no longer a stranger, because they have a history attached to that transaction. Think about credit reports, who've been around for many years. It's remarkable. You can walk into town where you know nobody, and nobody knows you, and you can say, "I'd like to borrow $400,000 for a mortgage." And that's only possible because there's a computer in the middle of the transaction that's capturing all elements of your history with respect to credit behavior. I just had dinner last night with a friend of mine here in Chicago, who started a .com called TalkTix. And what it involves is selling tickets. It's a little play on words of TikTok. But the idea is you can buy a ticket to go to a restaurant at 5:30 on Tuesday afternoon when there's not much business, and it's a very attractive price. And if you try to buy a seat at the same restaurant for Friday, Saturday, it's a higher price. But you are able to do this transaction, which would be fairly complex to do just over the telephone or via print. You can do it on the web very, very easily. And of course, it gives you a much better allocation of resources because you can use that underutilized time and capability in a way that wasn't possible before. So let me say a few words about the big data and econometrics, because I think we're going to spend a lot of time talking about that. There's a lot of work in big data that I think is just fantastic, but I don't think economists have too much to contribute to it. So these are things like image recognition, voice recognition, computer translation, entity identification, and so on. And people are very excited about new techniques like deep learning, which is kind of a network of neural nets that allow you to do that kind of identification. And machine learning is focusing primarily on prediction problems. Whereas when we think about statistics, we're also interested in summarization. I mean, a lot of statistical analysis is really data reduction. We're trying to understand the patterns. Inference, we're trying to estimate some parameters. Testing, like I discussed before with the continuous improvement. And finally, causal inference, which I like to think, and I know Susan thinks, that economists have an edge in that because we've been doing it for so many years. But when we look at the techniques that are involved in machine learning and we say, how can we use those in our own subject, I think there are several important aspects that come out. One is nonlinearities, particularly thresholds and interactions, because lots of times in economics we have a limited amount of data. We choose simple models, sometimes too simple, and we miss some important nonlinearities, thresholds, and interactions, where machine learning systems can identify those more easily. Thinking about model uncertainty as opposed to sampling uncertainty, we're kind of focused on this idea that we're drawing samples and how our estimates change with different samples. But in many cases, I think it's more appropriate to think about the modeling uncertainty, which is, especially if big data, is a lot more important than the sampling uncertainty. And then along with that are the issues of variable selection and model selection. Lots of times now we're dealing with what I like to call fat regressions. There's many more potential predictors than there are observations, and depending on where and when you took statistics, people would just say, no, we don't deal with that case. But now we're forced to deal with that case because we have so much data. People are rightly asking, what do we do with all these possible predictors? How do we figure out what's best? How do we avoid spurious estimates and so on? Model averaging, which I referred to in the Netflix example, economists actually invented model averaging because very early on people noticed with big macroeconomic models that the average of the forecast tended to beat any one of the models. We never followed it up in a very effective way. And now there are, I think, very interesting techniques for doing that. Overfitting, very important theme in machine learning. We don't pay enough attention to it in economics, in my view. And finally, the methods that Susan alluded to, the train test cycle and cross-validation, which are very, very useful techniques for analysis. And finally, the last thing, which I believe is very important, is computational Bayesian methods, where Bayesian statistics and Bayesian econometrics has been around for many years. But given this explosion in compute power, we can actually do all sorts of things that were just infeasible before. And it turns out to be very, very helpful in all of the cases I mentioned, in doing the model averaging and doing the variable selection and so on. So there's I can only echo what my colleagues have said. There's a lot of exciting things ahead. There's a lot of possibilities for cross-fertilization here. I think it's an exciting time to be an economist. Thank you.
So
So thank you, each of you, for starting us off. You touched on many points that we're going to circle back to later, but I kind of wanted to take a step back and note that each of you have very different backgrounds, even though you're connected by this involvement with big data. So Professor Varian is an economist with a background in information technology. Professor Athey, you have an auction theory background, and Professor Wasserman is a statistician and machine learner. I'm wondering if you could briefly sort of tell us, how did you get to where you are today, and what role has big data played in shaping your careers along the way?
Well, I'll start out on that, because I guess I've been doing it for a long time. I'd written a book called Information Rules, along with my colleague Carl Shapiro. It was about how to use economic analysis for high-tech markets. And Eric Schmidt was a fan of this book. And I bumped into him at a meeting. He told me, I just joined this cute little company down in the South Bay called Google, and I would like you to come help us out. So I went to Google. There were about 300 people there at that time. Had a great day meeting people, finding all the exciting things we're doing, and so I signed on to spend a year there as a visiting professor. So I had a year off from Berkeley. And I asked Eric, what should I work on? He said, well, why don't you take a look at this ad auction? I think it might make us a little money, which was kind of the understatement of the decade. So it turns out that I looked at the ad auction. I was convinced this was something that was out there in the literature somewhere. We just had to find it. I looked in the literature. Nope, wasn't there. I had to figure it out by myself. So I worked on the ad auction, and it turned out to be very helpful to have an economic analysis, kind of like Susan described, of how economists think about auctions. And it was very helpful in terms of evolving that auction. And along the way, when he's kind of got that work finished up, somebody came to me and said, can you help us do forecasting? And I said, well, what do you do now? And she said, well, we highlight this number in Excel, and then we click on the button that says forecast. And I said, well, we might be able to improve on that a little bit. And finally, that summer, we noticed that the queries to Google were dropping dramatically. This was back in 2002. And everybody was really worried. They said, oh, well, game is over, better dust off my resume and that kind of thing. And I looked at the data and said, you know, why don't you plot that data in logs? And they did. And sure enough, you could see right away that the drop this summer was just the same proportionally as the drop last summer, which was just the same proportionally as the drop the summer before. And so they said, how did you know how to use logs? I said, that's what they teach you in econometrics. So they decided that I might be useful to have around, and spent this time working on forecasting advertiser behavior, user behavior, all sorts of issues. That's how I got into it.
Very good. So maybe I can pick up from there. So in some sense, my entree was a little bit parallel to Hal's in that, so I had been working on designing auction-based markets and marketplace design for a period of time, matching up theoretical economic models to data. And so there, one of the things that I had really focused on was sort of how the design of the auction affected who participated in the marketplace, so that different auction rules might attract big bidders versus small bidders. And so I was able to use models to do things like predict what would happen if you switched from one auction format to another. And I had some nice data that was experimental data where I could show that my model did a really good job predicting what happened. So this was sort of the type of work I was doing. It was very small data work. But then Microsoft was very worried about how to compete with Google. I think somebody told Steve Ballmer that Google had a chief economist, and that sounded like a good idea. So he read an article about me in the Harvard Alumni Magazine, because I just moved to Harvard and gotten this big prize, and it talked all about using data to understand marketplaces. So they called me up and said, I got this telephone call, would you like to come meet Steve Ballmer? And I said, okay, sure, what does he want to talk about? And they said, well, we'll see. So I went out there, and they brought in all the executives from the advertising business and basically said, well, you seem pretty smart. Help figure out how we compete with Google. And so, as I went in to start working on this, at first the natural things to think about were the auction, and I think the engineers and the machine learning people there were very good at doing the basic prediction to make a search engine run, but they had only been running it for a short period of time, and most of their energy had just been put into sort of making the thing work. It could accept orders, it could accept bids from advertisers, it could present results, but they really hadn't spent a lot of time thinking about how to optimize it yet because it was sort of still pretty young. And so, I think they understood that I was going to help them with auction design, but actually the auction design problem wasn't really that hard because it was a smaller search engine, and the main thing they should just do is copy Google and be as compatible as possible to make it easy for advertisers to port their campaigns. So I first said, well, fine, don't do anything creative, and that was kind of disappointing for them. Just, copy Google and make it just so the advertisers will find it easy to come. But actually, it turned out there were lots of other really interesting issues where I don't think they had expected an economist to be helpful, but where I was very helpful. Because actually, from an engineering perspective, they tended to think about the advertiser order database is it's like a database. It's like something that I call. I have an algorithm, and it's going to maybe change something about how the auction is functioning. But there's just this order database there, and I'm going to take that as fixed. And to an economist, that's like the craziest thing in the world, because we think of those as active bidders in auctions who are responding to what we do. And if the prices go up or the prices go down, they get more clicks or less clicks, they're going to respond. These are active, living, breathing things that are optimizing some objective. And so if you're trying to grow the marketplace, you need to make them happy. You need to measure their welfare. You need to predict what will happen if the world changes. And so this actually, I spent years arguing with machine learning people who either thought that what I was talking about made no sense, or it was unnecessary, or if it was important, they could just throw a really big prediction model at it and say, well, just look at what the advertisers did in the past, and my model is smart. It's a neural net, blah, 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 or it's this, that, and the other, and it's going to predict. And so actually, they really didn't even have a language or a conceptual framework to say why that was wrong. And it was completely obvious to me why that was wrong, because they were operating, whatever the patterns were in the past, those were operating with a certain set of auction rules, and if I changed the auction rules, they would change their behavior. And that's, of course, that's like, econometrics 101, but that was completely not even in the realm of possibility. And then once I finally convinced them of that, they said, oh, wait, you're saying the world really changes? Really changes? And I'm like, yeah, the world really changes. And they're like, oh, well, then you just retrain your model. But, you couldn't possibly learn anything from data in one world and predict what happens in another world. That's out of scope. That's not even science if you say you can do that. In fact, you're a charlatan, you're a magician. And so to sort of say, well, actually, it's neither, it's absolutely hard. But it's not impossible. And there's actually a science about trying to understand what assumptions will make that a good exercise and what assumptions will make that a bad exercise. And that's the whole thing that I do. That was really novel to them. And I have to say that I don't think I ever convinced most of the people. But at least, a certain set of people, the ones that needed to really understand advertisers, learned that there was a different way to think about things. And I would say just more broadly, even when working on a problem that's not incredibly economics in nature, I found that my training was very good at bringing conceptual frameworks to problems. That's what the social science training is. It's what should I measure? Why would this measure be better than that other measure? This one's noisier. This one's more correlated with long-term success. This way of measuring things is going to be easier to visualize, or it's going to capture it's going to align incentives better. This is all very natural for me to think about, and this was very unnatural to folks from a different background that was more a mechanical background. And so in some sense, this is why I'm excited to be teaching in a business school now for the first time. I think it's really important for the business world, for people with the social science training, to get enough technical skills to get out there in the world, because actually, Google's doing great, but they would do even better if they had more social science people in there, and a lot of these other companies as well. They make systematic mistakes because they're mostly being run by people who don't really learn how to think the way we've been taught to think.
So my entry into the world of machine learning was quite different. I was the typical statistician sitting in my office proving theorems about non-parametric estimators with, dimension 3 and things like that. And then just by chance, I happened to be at a place where there was some smart people in computer science, Tom Mitchell, Andrew Moore, a few other friends over there, who came to us and said, we're going to start this center which brings together statistics and computer science. We think this is really important. This was quite a while ago, so they were really forward thinking. And they said, would you like to be part of it? And my first reaction was, what do I want to do that for? That's not going to go anywhere. Well, luckily they talked me into it, and then they got lots of other people from statistics involved, and it grew into eventually this Department of Machine Learning. And I got into it really through theory. At first I just got very interested in exactly the kind of problems Hal was talking about, where you have more features than you have data points. These high dimensional problems, just for me, I was very interested in the theory. I was working with a guy by the name of John Lafferty, who unfortunately, for me, left CMU and came here. And everybody here should take John Lafferty's course in machine learning. And so I spent years with John developing. It was great working with him because he knew all the CS and I knew the statistical theory. And so I was more into the theoretical end of it and kind of porting over the theories, the asymptotic theory and so on that we knew from statistics, and trying to port it over into machine learning. And I did end up getting involved sort of in larger scale projects, but oddly enough, not through the CS department, but mostly through my work with astronomers. But I've never been involved in these social science kind of things, so I have a very different background.
Okay, well, thank you. I think I wanted to touch on a point that Professor Athey touched on in her opening remarks on this balance between causality and prediction in econometrics going forward. Professor Varian, you've written papers about the difficulty of extracting causality in high-dimensional data sets. But I also think it's interesting to note that a lot of the companies that are working with big data are largely producing predictive results. So, for example, we see Facebook utilizing facial recognition software to predict who's in a picture before we even tag them, or Amazon and Netflix using these algorithms to say, oh, well, they viewed this and they purchased this in the past, what are they going to want in the future? So kind of two questions. One is, can we derive causality in high-dimensional data sets? And two, is this an objective for companies when they're using big data for business results?
So, and just to start with, actually, there's some of the kind of popular examples of prediction actually do have a sort of causal component. So for example, one of the inputs to the Google AdWords auction and the Bing's version of that as well is that you have to predict clicks. So I want to say the bidders pay per click. So if you want to figure out how much revenue you're going to make from them, you have to know how many clicks they're going to get. So they bid per click, but they're going to pay their bid per click times the number of clicks. You have to predict the number of clicks. So the click prediction algorithm is really important. But what is a click prediction algorithm? Well, I've seen this ad. I might have seen it in position 3 once, in position 5 once, and so on. And if a new query comes in, I need to understand, well, what would happen if I moved that ad to a different position? That actually is a causal question. It's saying, a counterfactual, what would happen if I saw this in a place different than what I did before? If I'm trying to lay out a screen, essentially I need to I could say I could rank these 1, 2, 3, or ABC 1, 2, 3, or BCA. There's lots of different ways I could do it, and of course, no matter how much experimentation you do, you can't possibly try out all the combinations and literally just learn it from data. So you're doing this kind of extrapolation, these counterfactual changes. And it turns out that actually you in principle would do a better job at those if you understand that aspect of the problem, rather than just thinking of it as a sort of a blind prediction. We'd also say, the companies like, the e-retailers, of course, are thinking about price elasticities and how much should I charge, and they're thinking about long-term retention of users and so on. So they often, I think, the most successful real-world companies will bring together kind of business analysts or economists with statistician or data scientist, machine learning folks. So one group, it might be better at actually carrying out the analysis on large data sets, but another group is good at sort of thinking about what the question should be. So, I mean, other things in the business world, you want to say, did this marketing program work? I need to counterfactually know what would have happened if I hadn't done the marketing program, right? So really, many business analytic problems and most types of analysis that's produced for executives in a data-driven firm are really questions about causal inference. The fact that you have lots of data means that I could ask, well, what's the price elasticity for each of 200,000 segments, right? But ultimately, I cannot figure out what a price elasticity is. I cannot understand how changing price changes demand unless I've had some sort of randomization, some kind of variation in the data. And as just you said, the identification, that is, can you actually answer a question, doesn't have anything to do with how many data points you have. Of course, if I want to answer it for 200,000 segments, I better have a lot of data. But ultimately, for each of those 200,000 segments, I had better have seen some variation in price that wasn't related to the fact that it was Christmas.
Definitely. And I don't know if Professor Rain, you wanted to add on to maybe the difficulty of extracting then. Yeah, we have so many data points. You touched on variable selection, these other issues that we have with extracting the causality.
Well, I think it's really what you need to do is look at the part where I mentioned continuous improvement and experimentation, because we, and I would say most engineers, are quite amenable to the idea that you do an experiment to really find out what causal effects look like. And so we've got, on the one hand, this observational data where you're looking at it, trying to gain insights, recognize patterns, and so on, perhaps formulate hypotheses that you would then test using this kind of experimental infrastructure. There is a kind of nice in-between place where economics sits, where we have natural experiments and we have ways to look at observational data, and at least in some cases try to extract causal inference from that observational data. That's the part that I think most people don't understand. It's something that's a sort of subspecialty that we've tried to figure out, because we're forced to do it. We can't go out and experiment with entire economies. So we have to try to infer something about what would happen if we did change an interest rate, or we changed a tax, or we did this or did that, because we've only got the observational data in most of those cases.
Let me just to expand on that a little bit. So in the business world, you actually kind of have multiple disciplines within data. So there's people who are doing A/B testing, randomized controlled experiments. Group A gets this treatment, group B gets this treatment, and we compare them. That's sort of, that might, for years, that was like people got different catalogs and different zip codes and so on. So that type of experimentation has happened for a long time, but now for the data-driven firms, it happens 10,000 times a year. No change happens at Google without going through an experimentation pipeline. So that's one kind of, and that's of course very focused on causal inference, and it's very obviously focused on causal inference because you're doing an experiment to see, does treatment A cause a change, right? Then there's this another, like the other extreme side is like this kind of very unstructured, large-scale machine learning that's kind of going into the composition of the web page. And then this sort of third thing in the middle, which is closest to economics, is like the business analytics, where somebody's going to present to the CEO and says, should we enter this new market? Should we cut our price? Should we keep doing TV advertising, or does it not work? And that's the part that's closest to what we've historically done.
I see.
So we're going to take a little bit more of a technical turn now. Increasing the sample size is known to be one of the easiest ways to increase the statistical power of a test. I'm curious, can you guys give us some examples of ways in which established statistical methods, so familiar methods maybe from an intro to statistics class or an introductory econometrics class, would be made more powerful by applying it to a larger data set?
Well, I'll take a quick stab at that. I think everybody will have something to say on that question, because there are many aspects to it. There's two parts to big data. One is having more rows, and the other is having more columns.
Of course, right.
And having the more columns, or the more features, are the ones that I think are in some ways the most interesting because they're the least well understood. The idea of increasing the rows or observations, well, we've got a lot of experience with what happens to estimators as you do that, and a lot of good theory as well. So I guess my view is that we have such a wealth of data now in companies like Microsoft and Google that the usual sort of sampling variation issue is not the most relevant one. The usual question is, do you have a good model, or maybe more appropriately, a good set of models that you can use to apply to this, this data?
See, I mean, one thing that actually one of the things I was doing was kind of a lot of modeling of advertiser behavior, and it turned out it's really highly heterogeneous. And so I was trying to, I sort of started running regressions, and then I said, well, let's make segments, and let's make more segments, and pretty soon I had like spreadsheets that had 1,000 regressions, and of course I had thousands of machines, so I could run 1,000,000 regressions if I wanted to, all in parallel, and look at the results. But at some point, and of course everyone had like very tight standard errors and so on, and at some point you look at all of this and you say, actually, like, this standard error thing is just completely meaningless. And so then I would kind of also, in parallel to that, I'm sort of arguing with my machine learning friends to say, I'm saying, well, gosh, your method, like, there's no properties, I don't know how to do hypothesis tests. But then they're like, well, why are you so excited about this little standard error here anyways? Because it's like basically, 0, but you don't really believe that. And so this whole experience actually led me to write a couple of research papers, econometric theory papers, that were based around the idea, really from the point to say, they said, well, what is that standard error? And I said, actually, God, that's totally wrong. And actually, all the econometrics textbooks are wrong. They haven't thought about this right at all. For example, they're thinking that you're sampling from a population, but I actually have the whole population here. So that's clearly, I'm not imagining some other 200,000 advertisers who are going to plop down. And so actually, what's going on here? What is my uncertainty? Well, if I'm thinking about, just a more economic example, changing a price, okay, I see the whole population of advertisers, but each of them was only experiencing one price level at this time. Mm-hmm. So the real thing I didn't know was not that some other hypothetical advertisers that don't exist, but rather I didn't see these advertisers experiencing different counterfactual levels of prices. And that's the source of my uncertainty, and that's what I should be focusing on. The other thing that Hal mentioned, which I completely agree with, is that actually the model specification, it was the fact that I have the wrong model is my real problem, not the fact that I don't have enough data. So we have a paper in the Papers and Proceedings this year that has it's kind of a machine learning inspired method to systematically check the robustness of your parameter estimates across a set of related models. And you can compare the standard deviation of your, say, elasticity estimate to the standard error. And so what we found is that in studies that were really well identified, either randomized experiments or that had really nice natural experiments, the standard deviation of the estimates was low. But in models where you use very fancy techniques to correct for sample selection bias, for example, the sensitivity was huge, and if you changed your model, your sign would flip, and the standard deviation of the model estimate was much larger than the standard error. And so, of course, we always could have thought about those things, but you're really smacked it in the face when you see like a standard error with like 6 zeros after it or whatever, like t-statistics with 10,000. Like, this is bullshit, this has nothing to do with the actual uncertainty that I'm facing. And then once you're faced with that, you rethink everything. And if you actually write down a formal model and really honestly say what your problem is, the math of how to solve it can fall right out, and you realize that you can think about things quite differently. So it's basically, that large, when the n gets really large, it focuses you on what's important in a sense.
Yeah, and I would just add, I agree with all that of course we start every statistics class with x1 to xn or IID from some distribution. And at some point in the class, I always stop at some point in the class and say, who's drawing these observations from a distribution? They're just numbers. They're just vectors. They're not and it blows their minds. They can't, we so brainwash the students that they are unable to think about data as anything other than this draws from this distribution. And it's especially true when you have these huge data sets which are very heterogeneous. Nobody's sitting there drawing them from IID from some distribution. So you really have to rethink the foundations. And then the other thing is, I think the model selection uncertainty is something we're very concerned about now in statistics, because I don't know if you guys would have learned this yet, but there's like the standard tool now in statistics is called the lasso, L1 regularization for doing a huge regression. And my sources tell me, I won't ask how, but that like when you do a Google search, you're doing a logistic regression using the lasso with zillions of variables. But if you do want to get standard errors there, it's not clear how to compute them. And we're still arguing about it. There's just been a couple of papers recently about proposals to do this, but there's very, very little actually known about that. So the whole idea that we know everything becomes easy just because n is big, I think there's a lot of complexity still.
Okay.
Maybe one other application of this is actually network experimentation and network analysis, which is getting really popular, and especially Facebook has a great data science team, and so people have been doing academic published research on Facebook data. But there's a lot of people on Facebook, but guess what? Like nothing's independent. If I shock some people, they're gonna propagate through the whole network. So a really interesting area, and this is also something that I've been working on, is even if you did a randomized experiment. So forget about endogeneity of who decided to post what pictures. But if I randomly show people get out the vote buttons, or if I randomly assign people to more or less ads. How would I test the hypothesis of whether that had an effect when I don't have any independent observations? And so there's a really exciting new statistical and computer science and econometrics literature on that topic.
Mm-hmm. Thank you. So I've got a follow-up question for you, actually, Professor Wasserman. I'm curious, since this is your background. Professor Athey has brought up cross-validation. Professor Varian brought up kind of the test and train cycle, which are methods for dealing with model selection and dealing with various kinds of issues like overfitting. What does statistical learning theory and statistical theory have to offer, in particular about kind of proving things about how we can pick our models?
Well, it depends what the goal is. If the goal is pure prediction,
okay.
If you don't care about explanation, but you just care about prediction, there's some very beautiful theorems that say that cross-validation actually comes with very high probability, chooses the most predictive model. And so that's very beautiful. But again, this is assuming our very pristine IID world. And I think when we leave that world, I don't think much is known about it. But also there's a different question, which is explanation, because the most predictive model often is a bigger model than you want, right? So if you're just minimizing prediction error, it's generally favorable for the prediction error to include more variables than you want. Whereas if you're thinking causally, you really want to know which variables matter. Right. And I think in those situations it gets much more, you're back in the world of causal inference with all its difficulties. Mm-hmm. But so I think cross-validation is a really good tool when you're interested in prediction and when you're, the data are kind of homogeneous.
Okay.
So I'll just throw in a little ad that the paper I presented at the National Academy 2 weeks ago was trying to take some steps towards using cross-validation to systematically do causal inference. But it's not actually obvious how to do that. So I don't claim to have solved that problem, but at least have taken some steps in that direction to try to combine those. But so this is one of the reasons why this is such an exciting time for science, because mm-hmm. you come on these questions that haven't really fully been answered yet, because mm-hmm. it's just, we didn't need to answer them 20 years ago.
Mm-hmm. Okay. So Kayla and I have a lot more questions about kind of the technical statistics, but I wonder if we maybe want to jump ahead to talk about privacy.
Yeah,
because I know that
it's a big topic.
I think that's something that we could spend a lot of time on.
Yeah, so a lot of our questions when we fielded some register questions were on privacy, and I think that it's natural because as companies are getting more and more data about consumers are naturally going to be having these questions about data privacy, security. Professor Varian mentioned the Netflix Prize in 2006. Researchers from the University of Texas at that time were actually able to combine that data with public data from IMDb to identify the supposedly anonymous individuals in that public data set that they released for the competition. And privacy concerns have also been released about Facebook and Uber and Venmo more recently. So I'm wondering if you guys can comment on the technical, but also maybe the ethical limitations that this trade-off between consumer privacy and analytic accuracy present
Look, well, I guess
the stars aren't that worried about it, right?
Okay,
Well, it depends. Some stars are.
because Hal and I were just talking about this before the event started, which is, there's this thing called differential privacy, which was invented by Cynthia Dwork and Adam Smith. Not that Adam Smith, although what a great name to have. But, and it's very ingenious, and it's basically, it imagines, if you imagine an opponent who has access to an arbitrarily large amount of information you don't know about, and you want to make the following guarantee, that no matter how much extra information this person has, when I release this answer, if he were to do a hypothesis test, is Hal variant in this data set or not, any test with type 1 error alpha would only have power about alpha. So there's no hypothesis test to test whether a certain person is in there. And so it's a very simple idea, actually, and very beautiful idea. But, so I actually got interested in this and started working on it. I wrote a few papers on it. And you quickly discover that as soon as the problem gets a little bit complicated, you, loosely speaking, think of it as just taking your data and adding noise to it. It's a little bit more complicated than that. You have to add a lot of noise. You have to dissolve the amount of information in the data set so much that it quickly becomes useless. And I got invited to this conference where there was cryptographers and statisticians. And the cryptographers were saying this is the only way you can do privacy. You must use differential privacy, or some smart cryptographer is going to do what they did to Netflix. And the statisticians are all going, this is insane. How can we add this much noise to our data? You'll never learn anything from the data set. And to make matters worse, most of the CS theory papers on this have this query response model where they imagine that there's a curator, and you send the curator a question, I'd like to know the mean, and he takes the mean and adds noise. Now I'd like to know the best linear classifier, and he takes the linear classifier and adds, and they can promise you these privacy guarantees. And I was trying to explain to them, when I analyze data, I don't have a fixed set of queries. I want to get the data, I want to fit models, I want to look at the residuals, I want to do goodness of fit tests, I might think of other questions as I go along. There was really a split. There was these two cultures. There was the statistical group there, and I suspect I don't think there was econometricians there, but if there were, I suspect they would have been with the statisticians. And there was the cryptographers, and they really were talking past each other. And I think, as far as I know, I actually haven't worked in the area for a few years, but my understanding is they haven't come together, these two groups, as far as I understand it.
So actually, I also saw Cynthia talk and also had exactly the same reaction, but then one of my colleagues, Denis Nekopolov, actually did try to write an econometrics paper where the goal was to estimate a parameter, and basically what he showed was that if you respected privacy, you wouldn't ever be able to get a point estimate, but you could get bounds. So to try to bridge that divide. But this, I think, is just an example where you have these different disciplines coming together, and if you can actually become bilingual, then you can have really innovative new research or in the business context, you can discover something very important that other people hadn't discovered before. Mm-hmm. So I think, just kind of bringing it on to the general, another related topic from more the research perspective is, how can academics work with, if most big data sets reside in corporations, and it's not, forget about like shipping a hard drive with the data. I mean, I can't afford 50,000 hard drives to take the raw data, so it's not, and I don't have the compute to take a mean, so it's not very useful to actually ship out data. A lot of times people are having to go in and work with companies to get the data, and what does that mean for science? What does that mean for reproducibility of the science? Just an example, the paper I present at National Academy, where they're going to have an issue in the proceedings of National Academy of Sciences, but they want replicability, and so I'm going to pull out one of my applications and put in something else because that's kind of hard to navigate. I can't make the data available necessarily. So there's actually this sort of science of science thing right now of how do we do rigorous reproducible science in an environment where the very raw data nobody can guarantee. It's too expensive to, in the very raw form, keep and maintain all of the data that you did your analysis on. And so, of course, that relates to privacy, because then some of my colleagues were like, oh, well, we should convince companies to send data out. But actually, there's a hat of mine that says, no, like, we shouldn't send that data out. We should figure out other ways to have it be reproducible, because actually, from the user perspective, having it's actually, you don't want the companies to be sending out your user data to researchers, even very trustworthy researchers. And so, you know, how we navigate this, we have these steel rooms where you check your cell phone at the door and come in and do your analysis, or, you know, whether companies have protocols for preserving data that's been published. You know, there's lots of different things that we're all thinking about right now collectively, so that the science on big data can continue.
I have to say I'm a big fan of the clean room, which you were just alluding to, because that's been used historically for many years. It's worked quite effectively. The Bureau of Labor Statistics, Census, they all have this kind of access to data under controlled conditions. We had a set of data at the University of Michigan when I was there, which was some very lightly anonymized tax returns, which could pose a privacy threat. But you could access it only in a sort of windowless room with a computer, with no USB, no disk drive, nothing, just a printer. So you did all your analysis in that room, printed out the results, and then you could go build that in your papers. And if you wanted to reproduce it, well, if you were a legitimate researcher, you had access to this data as well. That's a low-tech solution, but it's pretty darn foolproof for most purposes.
And you don't have to add a ton of noise to the data.
Exactly.
Yeah.
Exactly. Yeah. So exactly, this whole like kind of noise thing does seem suboptimal. And so I think, though, more broadly, you know, maybe you're trying to get at the big policy issues that are in the paper all the time of, you know, balance between, you know, privacy and service. And I think some of the things that are really challenging for making public policy around privacy is that actually consumers don't really know what they want. And if you try, and most of the time economics thinks that, well, we can learn what people want by revealed preference. But actually some of these concepts like privacy are really hard to measure from revealed preference either, because people don't really understand what they're choosing, or they might just think, well, you know, I don't trust any of these guys, and I can't, how would I know whether my data is safer at Facebook or at Google or where else? Any of them could get hacked, or maybe they're all spying on me anyways. So, you know, it's very hard to kind of really understand how consumers would feel about counterfactual worlds. And you yourself as a consumer wouldn't really know until you lived in that world for a while. You know, I mean, if somebody had asked me about putting the contextual ads on Gmail, that, you know, where they read the keywords of your email and put up ads that respond to those, you know, my business advice would have been that, you know, consumers will hate that. You know, they'll flee en masse. This is a terrible idea. And for that matter, maybe if Microsoft had done that, people would have hated it because they had a different feeling about Microsoft. But, you know, Google did it, and, you know, was it that people liked Gmail so much better that they put up with it, or was it that they really didn't care? Was it that they got used to it? You know, it's actually very hard to really get precise estimates of what people want. And so, you know, the other thing that gets, though, in the absence of, we don't have great data, but then also when you go to talk to policymakers, like I went and gave a talk about this in Europe to the Dutch government. You know, at the end of my talk, which was all about cost-benefit analysis of privacy and the problems of having, you know, too strict or too loose privacy policy, the first person who stood up was a lawyer who said, "You were talking about cost-benefit analysis. You don't understand. In Europe, privacy is a fundamental human right. It doesn't really matter what the cost-benefit is." So, okay, you know, where do you go with that? I mean, you know, if you wanted to continue to be a fundamental human right, maybe you need a democracy. And if you want a democracy, maybe you need newspapers. And if you want newspapers, then maybe they need to do some advertising. You know, and so there must be some, you know, some relationships here. But you know, there's really this whole debate has not had a lot of economics injected into it. And economics has had very limited impact on policy. So as a result, our policies, you know, are sometimes, they look like lawyers wrote them. Like you go to Europe, and if you look at every single website, we have cookies, we have cookies, we have cookies, we have cookies. Like, does that do anything for user privacy? You know, no, it just annoys the heck out of everybody, and they stop paying attention and just click the button until it goes away. You know, and obviously this was not a policy done with sort of cost-benefit analysis in mind.
Yeah, definitely.
Actually, I read an interesting paper recently by Ben Witz and Jody Liu, a couple of economists at Brookings, and I'm going to paraphrase what they said. It says, search engines are the best thing that ever happened to privacy. That's my own interpretation. But the reason is, let me tell you the reason. There are a lot of queries in the form, how do I know if I'm pregnant? How do I know what the symptoms of herpes are? What would happen if I did report some income on my tax return? On and on and on. These are questions that people would not ask to their parents, to their doctor, to their lawyer, to their accountant, to their friends, because they were concerned about embarrassment or privacy issues. But now, really for the first time in history, you have this definitive way that you can go out and ask a private question and get a pretty good answer to all those issues. And that's not something that's really been available before.
That's right. Now, of course, hopefully, if I trust anybody to keep all of this secure, I mean, some of the US tech firms have really good security, but some of that data is sitting on a server somewhere, and actually, if you haven't changed your settings, your Google searches from 2007 are sitting on a server somewhere. So this is a combination of security and privacy. That some intern somewhere, or some hacker somewhere could actually get those and post them on the web. And of course, you're a random person who cares about you, but for all of you, somebody cares about you. And so I'm sure for all of you, if all of your Google searches from now back to 2007 were on the web, there would be something there that you would be unhappy about. And so, there are, a lot of questions about, well, how much data needs to be retained, and, can anybody promise that it's safe? Is that even plausible? And basically, we don't think that anything connected to the internet is really safe from incursion at some level. So, would I rather have one company have all my data and be really good and have a lot of incentives to take care of my data, or would I rather that everybody have just a little bit so that any leak of my data would not be that devastating to me? So I don't think none of this has really, I think, super clear answers.
And there's also the important issue about self-help, namely, to what extent are you responsible for choosing good passwords, changing them relatively frequently, not using the same password on all your accounts, and on and on and on. I mean, these are things that, because the internet is relatively new, many people aren't aware of what good hygiene looks like when you're doing this kind of activity. But you all, I hope, are following good practices in this dimension. And if you aren't, you should go do it.
Okay, well, yeah, thank you. I think it's a really big topic, and you can access it from a social welfare perspective. You can access it from a purely statistical and computational perspective. But I think that one thing it really reveals is sort of the relationship between the academic nature of the question and the private sector implementation. And I think that throughout our discussion today, we've sort of seen how the two go hand in hand. I mean, maybe originally we saw, and I don't know if this is true, but maybe originally we saw academic researchers sort of propelling a lot of the advances that we see big data utilizing at companies like Google and Microsoft. But it seems like today maybe researchers are using the data from companies like Google and Microsoft for their own advances and using the methods that companies are developing. So I'm wondering if we could sort of explore the relationship between academia and private sector implementation, and maybe where you see it going in the future.
And part of that has to do with researchers accessing data that's gathered by companies. But the other part of it, of course, has to do with researchers and people in companies using technology that's developed in companies and then later open sourced. So things like Hadoop and Cassandra, which are open source implementations of software frameworks developed at Google and Microsoft and other tech companies. So they're kind of several different sides of this question of academia versus the private sector.
So just say on the positive side, this is a moment where a lot of science is happening in industry, and so that's or in collaboration with academics and industry, and that is happening for a reason. It's because there's no lab version of Facebook. So if you want to do an experiment on 200 million people, like, you're going to collaborate with Facebook. And so on, the only places where systems of the scale we're talking about exist are inside companies, both for financial reasons and, of course, in some sense, it's in the course of making the products that they've invented all of these things. So it's an exciting time to collaborate, and of course what that also means is that there are lots and lots of companies that want to hire economists and social scientists and statisticians and machine learning people to work there. So there's much more interesting job opportunities in this area if you chose to go outside of academics. But also, because most of them are inventing this science for the first time, they really want collaboration with academics. And so, what are some of the kinds of science? The science of managing a marketplace. How do you measure a marketplace? How do you balance supply and demand in a marketplace? How do you think about the dynamics of a multi-sided platform market? That science is being invented by the companies that are inventing the platform markets. We had no science of search advertising markets before we had search advertising markets. And then the statistical science, the machine learning, the computational tools, it's all getting invented there. And so if you want to be on the cutting edge, it is necessary in some sense to collaborate with the places that it's happening. And so it's got the positive side that it's got the economists are able to get much closer to the real world problems, and corporations are letting them work with their data in a way that they wouldn't if they didn't see a huge benefit from it. Mm-hmm. So that's sort of the very positive side. Of course, you have to be concerned about conflicts of interest and replicability, and also I would think like kind of inequality of access. The Stanford graduate students right now have a huge advantage at this because they're in Silicon Valley, so their advisors are friends with the CEO and so on, and so or like HBS, they're not there, but they have all these connections, and so certain connected students and researchers can get access to this, and the less privileged can't. So all of these things concern me. I don't think it's a reason to stop doing the science. Maybe it's a reason to try to, one of the things I'm thinking about now is providing some public goods like Creative Commons types of contracts that researchers can have with companies so that they don't have to rewrite the non-disclosure agreements and the reproducibility agreements each time. Maybe we might be able to create some of these clean rooms as a central resource. So maybe one sits at Stanford and we can go and talk to the companies who are willing to share the data, but we might also be able to let graduate students or faculty from other places come in under our conditions so that we can expand access to all of this. And then the conflicts of interest can be tricky, and I think that's kind of a case-by-case basis because frankly no firm wants you to come in and do something that's damaging for them. At Microsoft, I tried to help people define projects such that the answer to the question was not sort of good or bad for Microsoft, and therefore it wouldn't have the appearance of conflict. And that meant, though, that maybe some very interesting questions would discourage researchers from asking because, even if you could get everybody at Microsoft to commit to see the bad answer, are people really going to be 100% sure that you weren't influenced in some sense by the company? So. And then the question is, well, what's in it for the company if you're only going to answer questions that aren't good or bad for them? So, in practice, what people often do is that they might kind of do a free consulting project for the company to learn about their data, and so that the company isn't sort of paying you to learn, and then instead of compensating you, they let you do a scientific paper that isn't conflicted. But these are very, tricky issues to navigate, and there's no rule book. Putting aside all of the, ethical issues and, am I evil if I make people sad on Facebook and so on.
Let me say a word or two about another theme related to this, and that is government data. Yeah. So we all use GDP and price indices and investment consumption, so on. But that data takes a long time to come out. GDP is only quarterly, and it's revised 2 or 3 times by the time it's actually stabilized. At the same time, Target or Walmart can tell you how much they made in each of their stores yesterday. You can go to MasterCard and buy from MasterCard for a modest amount of money how much was charged on MasterCard by region, by retail establishment. You can go to ADP or Intuit and get data on small business payrolls on basically a weekly, bi-weekly basis. So a lot of this data that we're seeing in the private sector is real-time data, okay? It's real-time data, and You compare that to the kind of data that's collected by the government, which is typically aggregated over a period of time. The natural question arises, well, how can we combine this real-time data from the private sector with the highly developed and generally very accurate data from the public sector in a way that really improves our understanding of the current and near-term state of the economy? So I think there's a lot of interesting questions surrounding that real-time data access for government and economic research.
Okay, so I think that we ran out of time a bit more quickly than we thought. But I wanted to close with a question that I think a lot of the undergraduates in the room really want me to ask. And Professor Athey, you touched on it by telling us all to take machine learning, and we know also take statistics. But I'm wondering, could you give us some brief advice on how we can best prepare for careers in big data as undergraduates? It's inherently an interdisciplinary field, but are there any fundamental skills that we should all be trying to acquire?
So yeah, in addition to what I already said, which I feel very strongly about, you should realize that you are potentially a rock star, all of you. In that, as I just can't emphasize enough how little kind of conceptual thinking the typical like developer engineer in a technology company is. You know, you've learned how to code, you've learned how to build things, but you haven't learned how to conceptualize how you would use data to figure out what you would be building. And so, you know, the role of like one economist, and like, you know, I think Preston McAfee, who has been at Google and Yahoo and now is at Microsoft, so like, you know, kind of the right ratio is like one economist for every 500 engineers or something, right? Because, but that one economist is incredibly important because you're the one who can figure out whether those 500 engineers are doing the right thing. So our training of how do you ask questions, how could you map data to a question and rigorously answer it? Like, what kinds of questions are answerable? You know, that type of stuff is what I see brilliant people not having good skills at. And so but then on the other hand, if you go in, and I've seen economists flail in tech companies, if you cannot pull data, if you cannot if you don't have good enough coding skills to answer your own question, pull the data, manipulate it, analyze it, and produce the results in a day or two, in a tech company you will fail. You will be fired. Even the MBAs, you know, Google, they say, my friend who works at Google told me that if the MBAs after a year aren't able to pull their own data, even if they're a salesperson, basically in a marketing organization, if they can't pull their own data and do their own customer by customer analytics within a year, they're dead. They're fired. So you can't even get a marketing job without being nimble with data. So I would just say, therefore, you have incredible things to bring, but you have to tech yourself up enough that you're not fired. More than that, maybe that you even get the respect of your technical colleagues.
Let me add one other comment to that. Because I think we would all agree that it's important to take courses and understand statistics, econometrics, and machine learning, especially given the composition of the group. So there would be little debate on that point. But then what else? Well, Susan said computer programming and computer design, absolutely. But another aspect that's very important is communication skills. Because remember, you pulled your data, you've done the analysis, you've done a brilliant job, but now you have to communicate it to somebody. And that includes both written communication, speaking communication, and visualization, which is a very important part of data analysis these days. So don't skimp on those aspects either. They're quite important in terms of career prospects.
So the economic theory and the economic training is part of what makes you particularly well suited to do that. Because we practice kind of mapping a verbal question onto a statistical model and then taking those estimates and bringing them back at the end. The policy conclusion is if the minimum wage goes up, then this many people will lose their jobs and this many people will have this much better outcome. That's what we do. That's what research papers in economics look like, but that's also what a presentation to a CEO looks like. And it's often the person with the economics or business background who can actually go in and talk to the CEO and be compelling I've been brought along. I got much more top executive exposure in Microsoft than I probably deserved, because I could understand everything that the technical people could do, but I could also answer questions about it in a very intuitive way to a very smart executive, but not one who wanted all the technical details. So you can be the one presenting to the CEO years earlier than you otherwise would if you can combine all of these attributes.
Yeah, I agree with all that, and let me just add that when I tell our students, I kind of preach to them exactly what you said. I said, learn how to code well and do it now while you're young. It's much harder when you're older. And I can't tell you how many students we've had go off in industry and come back and say, I wish I had listened to you. I wish I had really learned how to code well. Learn how to code well and learn how to code well right now. Don't wait. Honestly, it's really, really important. The other thing more technical, is convex optimization. Maybe it's getting a bit too techy, but I feel like that's if I could go back in time and learn something when I was young, I would be convex optimization. And I think who knows, maybe I'm wrong, maybe 5 years from now it won't be that important, but right now that seems very, very important. If you have access to a convex optimization class, I would take that too.
There's actually one being offered this quarter. So
there you go.
It may be too late, but.
So I and many of my colleagues have started hiring full-time research assistants, so people between undergrad and PhD. So I have 5 of them at Microsoft. We have 6 of them at Stanford GSB. Harvard has had a bunch of them. But over the years, as I've been doing this for 5 or 6 years now, I have stopped hiring any econ undergrad who doesn't have some computer science skill, because somebody who's just been a research assistant and done reg Y, X1, X2, X3 15 times is not at all prepared for the types of pipelines I have, where I'm scraping data and pulling it together, and I've got 10 steps to create my data and to analyze it. I really need students that have some computer science background, but the supply isn't good enough. But then if I take these students, I can actually get you into the Stanford PhD program or get you into a much better PhD program as a result of this mentorship. I can also expose you to big data in a way you never would, but if you don't have the coding skills, you're not useful to me. A lot of the people who choose to hire these research assistants are doing it because they have needs that are similar to mine.
Yeah, thank you. So we're going to open it up to questions from the audience now.
And because of the nature of how many people there are, we actually pulled some pre-solicited questions, and so you guys know who you are. And I also want to note that because the catering was a little bit late at the beginning, we had to move our reception, which was supposed to be at 3:30, to the end of the event, and so everyone is welcome to come join in room 112, I believe. So we still have the food, just a little bit later. So yes, John.
Microphone, or I can project.
Maybe project for now.
It's not a problem.
Oh.
Yeah, I just want to make sure people in the back can hear as well. Thank you so much for each of your excellent remarks. I thought they're all fantastic. I think the talk got really deep on microeconomics and big data. And I know we got a little bit toward this at the end, but I want to ask you a question about macroeconomics and big data. So I think we've learned from the MIT Billion Prices Project and Premise as well, and some of these other companies that are doing this, that we can track inflation in the economy pretty well, and that we can get pretty close to the BLS inflation data using aggregated web scraped price data from retailers like Amazon. For those of you who aren't familiar with what the MIT Billion Price Project, that's what it does. So my question to you is, do you think that we can extend this aggregated web scraping approach to tracking labor market variables? Could we have, say, a billion jobs project? And I know how you have some experience with tracking UI claims using Google search trends, and maybe kind of putting aside the retail data and the payroll data, because that's kind of been around for a while, but just thinking about aggregated web scraping. And full disclosure, I run a startup that's trying to do this, and to Larry's point earlier, we do employ a PhD statistician.
Excellent.
And I actually asked Paul Krugman the same question recently at a lunch, and he said that he thought it was a good idea, and maybe you could disprove the employment truthers. if you know what that is, if you follow Paul Krugman's blog. But he said that he wouldn't have any idea how to go about doing it. And as some of the world's best big data economists and statistician, do you have any ideas in how we can use big data to track the labor market in real time and with more granularity than, say, the BLS data?
Well, there is some interesting work. You mentioned ADP has been around for some time, but they've got a lot more data there than they've actually released, and they're thinking about how that data can be used in the most effective way. And Intuit has this very nice small business employment index that draws on QuickBooks data, which is very helpful because it's really hard to know what's going on in the small business sector, and it's a very important sector. So the data is becoming available. And I think there'll be challenges along the way, of course, but I think 5 or 10 years from now, we're going to have a lot more of this real-time data taken off the web or other private databases, private company databases that will enable us to get a much better picture of where the economy is.
I mean, maybe just also, LinkedIn, of course, is an amazing data source, and you'll think of LinkedIn as it's like a social network. As a consumer product, it's a social network, but the business of LinkedIn is actually that it's basically a phone book of the entire potential employee population for every corporation, and that's kind of how they make their money, selling access to LinkedIn. And because of the nature of the social network, people really do maintain their histories pretty accurately. And so, some people have tried to look at that already, but when you look from the worker perspective, that's a really amazing data source.
LinkedIn has an economic graph project.
Exactly.
I'm pleading ignorance on this one. But thanks for hiring a statistician.
Did we have any other questions from the audience? Yes.
Hi, my name's Aaron. I'm in the, great. Hi, I'm a grad student in the Harris School of Public Policy here, and something that I've been bouncing around for a while. I have no idea if this is feasible, but Professor Athey, you mentioned that people don't know what they want, and that might feed into this, but how, if you think about democracies and the role of legislators and their behavior, better behavior or more representative behavior might affect better outcomes in a democracy. So I'm thinking, is there a technological solution to help create a better, more transparent sense of voter preferences that a legislator might monitor and provide as a feedback loop back to their constituents so that we might have a tighter representation? Is that something that might be possible with the sort of, I guess, private data?
Well, it's too bad we don't have Nate Silver here, one of your alums, who, of course, has looked in great depth at what political data can tell us about consumer and voter behavior. I think what you say is possible, but I do worry a little bit about that, too, because voters are very fickle. And opinions change dramatically, and so much depends on how the question is framed or worded, that if you had too tight a feedback loop between the political representatives and their constituency, it could be perverse in a way, because it could make for policy that's not as well thought out or considered as might otherwise be the case. So this is a debate that's gone on for, several thousand years between democracy and representative government, where you've got the direct voice of the people versus representatives who are helping people formulate views and move policy forward.
So I'd say, actually, when I give speeches about big data, especially to business audiences, I spend a big chunk of the time talking about a theme that didn't come up today, which is sort of short-term versus long-term. So forgetting about whether they're short-term or long-term, some things are easy to measure and some things are hard to measure. So if you're trying to optimize and you have different measures, you tend to put more weight on the things that are easy to measure. If you had two equally important goals and one of them was easier to measure, it's easier to do rapid A/B testing and experimentation against the thing that's easier to measure, so you're going to get better at the thing that's easy to measure. So what that means is that most data-driven firms systematically innovate in a biased way. What engineer wants to work on a project that's going to look bad in an A/B test, and you have to argue that that'll be good in the long term? Everybody wants to work on a project that will look good in an A/B test, in a short-term test, and if it has any bad effects, those will happen 6 months later and nobody will know you caused them. So that kind of project goes through all the time, and the other kinds of projects are underinvested in. So why is this relevant? Well, there's lots and lots of different applications of this, but I agree with Hal that in some sense if you have too much feedback, you could actually encourage politicians to do even more short-termism. A more positive answer to that question, though, is that actually with technology, there's a lot more chance to interact with people, and we've actually found ways to gamify various types of engagement. So one of my colleagues at Microsoft did this thing during the last election where they surveyed people during the debates when they were watching them on Xbox. And of course, the kind of person who watches a debate on Xbox is the kind of person who likes to have a controller in their hand, and they feel kind of uncomfortable sitting there for a half an hour without pushing the button. So, you know, they actually liked watching the debate better when they could push the button. So they would pop up all these questions like, you know, okay, Romney just, you know, scored a big point, and then they would ask people, you know, how did your feelings change? And so they were actually able to do better than polls at understanding people's preferences. Also, because the people were logged in, they could watch them over time. They discovered, for example, that if you poll people right after a debate, the people whose guy won are more likely to take the call and answer the poll than the people whose guy lost. And so the cross-sectional polls were sort of systematically biased, and they could pick that up because they were watching the same people over time. So, you know, this was a new way to get information, but part of how it relates to your question is that, you know, actually, like, we like to interact with stuff. People are, you know, playing all sorts of crazy games on their phone. Why wouldn't they want to actually participate in their democracy on their phones too? And so I'm expecting that in the next 5 years, some bright young people like you will come up with some new ways to get people involved that will both create information and create participation and also hopefully educate them at the same time.
Great. Yes.
Thank you.
Hello, my name is David Abraham, and I'm an undergraduate student here. I'd like to thank everyone on the panel from coming out all the way to Chicago in the midst of this turbulent weather. Hope you're having a wonderful time. It's nice today, at least. My question is kind of stemming from Mr. Varian's book. From the last part of our 201 course where we talk about the social planner and the comparison with the general equilibrium problem. The main obstacle that we found was that there is just simply not enough information on consumers' preferences to automate an allocation and endowment-based economy. And so what I was wondering is, if we have such significant computing prowess to the point where we can, say, establish how much stuff is in an economy per se, and we have enough data on how people will interact with that stuff, do you think it would ever be possible to automate an economy using a computer?
Well, it's interesting. This is a very old debate. It goes back to the 50s and 60s with Longa-Lerner models of whether you could have a kind of market-based socialist economy and do these computations which would allow for you know, a more efficient system. I guess the current view is that's pretty utopian and unlikely to be achievable, because nowadays we understand pretty clearly that a very important driver of the economy is innovation, and innovation almost by definition is something that can't easily be predicted. And I think Susan made a very important point a minute ago when she was talking about the short run and the long term. All of us are taking actions now in our school, in our businesses, in the government that will have long-term repercussions, and those long-term repercussions are very hard to measure. So even though I think we've done a lot of important advances in computation, I think it'll be some time before we really have something that could be an effective model of a dynamic economy.
Okay, and I think we can, oh, there we go.
Hello, my name is Jörn. I'm a PhD student in economics here, and I have a question how you view the economics of the internet in a sense that when I was checking for a specific car at a specific time on Hotwire last time, and I used 3 different browsers, I got 3 different results for exactly the same query. That means you're using a lot of live customer identification tools, customer vectorization, and then you basically classify the customer, and probably companies assert a probability of this customer being more or less price elastic and assign very personalized prices. So in the beginning, let's say even 5 to 10 years back, everybody was very happy about the internet, thinking, oh, it's the greatest thing for consumers because consumers can now compare across like 100 different prices at once. But now we see this backlash into, or like this, like turning around of the power of data. Now it comes all back to the consumer being price discriminated on heavily by companies. And I would like to get your opinion on how do you view this to go down in the future? Like, do you think there will be a backlash from the consumer side? Do you think there will be more anonymity, like going into even anonymous browsing and stuff like that? Or do you not view this at, for example, Microsoft or Google as a problem at all? Because like it becomes more and more public knowledge that price discrimination is happening due to the data we share on a daily basis. And how do you view the future of that?
Well, I have to say you should be careful about your experimental design there, because what you want to do is you want to take each of these different browsers and access it in incognito mode, or delete cookies, or look at it without any history. What happens is companies are experimenting with pricing, just like we were discussing experimenting with search algorithms or ad algorithms and so on. At any time that you go on to Google, you're in at least a dozen experiments. So there's quite a bit of background noise, which I think in general should not be interpreted as price discrimination, but really searching for a kind of good price in terms of revenue maximization. As Susan mentioned, this has been going on with catalog sales and direct marketing and all sorts of other things for years. Companies have to have a way to experiment and try to estimate what that demand curve or demand elasticity looks like. So there's a substantial amount of that going on in the internet. I'm skeptical that there's a substantial amount of price discrimination because of the point you made. People don't like it. They don't like being charged different prices than the guy next door. There's a lot of bulletin boards. When Amazon did some experimentation several years ago, people interpreted this as price discrimination, and there was a big backlash. So I think it's a dangerous game to play, to really do differential pricing to a strong degree, but it's very common to see experimentation so that different users will see different prices, different times.
Yeah, when I have an experience like that, I'm always like, oh, I must be in an A/B test, or I must be in 10 A/B tests. But I think just to follow on to what Hal's saying, and Hal has made this point himself, that there's actually a constraint. From information economics, there's sort of the incentive compatibility constraint. So here the incentive compatibility constraint is that if deleting your cookies gets you better prices, then everybody will delete their cookies. So if you do too much of this, people will then try to pretend to be someone else. And of course, the last thing Amazon wants you to do is to open up a new account. It's much more valuable for them to have your entire history, because they're going to make much more money by being able to recommend things to you and get you to purchase something you didn't know you wanted than by raising the price a little bit. I don't want to say that it won't ever happen, or that it won't happen in an increasing way. And if somebody ever thinks they've got you locked in and you can't kind of change your identity, or it's really expensive to change their identity, then maybe they would exploit you somewhat. But there's a lot of things that kind of put the brakes on that.
Actually, this reminds me of an interesting story involving Orbitz, I think, which is here in Chicago, right? Isn't Orbitz based here?
So,
I think so, yeah. So there was a news cycle a year ago where they said they were showing higher price hotels to people who were accessing Orbitz using Safari, the Apple browser. And indeed, this was true, but it was because the people that were using Safari were more interested in higher price hotels. They didn't click on the bargain hotels, they were clicking on the ones that were, a step up. And so the question is it better to show the people the results are more likely to click on, or is it better to show them a kind of uniform set of results? And I think you'd argue as an economist, you'd probably want to say, let's show people the things that they're most relevant to them, and that would be the market segment that's most attractive. Now, is that price discrimination? It's a little hard to say, I think.
So the same thing brings up a larger challenge, and you said, oh, well, I used to often tell the story, saying the early days of the internet, so I use Hal as an example. The future chief economist of Google, wrote about, what was going to happen in the internet and information rules, but actually there was a lot of stuff that wasn't in there that that none of us, it's just evidence that even the best of us didn't anticipate all of this at the time. So like the ad-supported Google, for example, even Eric Schmidt wasn't sure that was going to be a really good idea.
Right.
But so we also thought, people writing all these papers about how there wasn't going to be any price dispersion on the internet and price was going to be equal to marginal cost. And I think what we didn't think about was the fact that, yes, you have a huge selection, but you're never going to be able to choose from that selection unless somebody aggregates and intermediates for you. It's the same with news. None of us type in a 500-character URL to get to a news article. Every single news article you read online has been curated for you by somebody. It's been curated by the New York Times, it's been curated by Google News, it's been curated by a combination of your friends posting on Facebook and Facebook choosing what to put first. It's curated by Twitter, and so on. And so all of your information is curated. It's curated by the search engine and so on. And so that has a couple of implications. First of all, if there's a small number of curators, those are going to have a lot of power. And there's huge economies of scale, and there's concentration in all things. There's not a lot of Amazons, there's not a lot of Googles, there's not a lot of Facebooks for sound economic reasons. So we're expecting a small number of people to be kind of a small number of entities to be having a disproportionate impact on what information you get about news, about prices and products and everything. So another fact is that if you experimentally, re-rank results on a search engine or re-rank things on a web page, you have a huge impact on what people do. So that the role of that curation, even in ranking the top 5 things on a page, is massively impactful. So that means if we start doing personalization, that's also going to be very impactful. But this is quite competing effects. Like, I've shown in some research about Google News that people who read Google News and get more customized information for them in the form of more local news actually get more engaged with news. So the search and discovery thing will get them to consume more, become more educated. On the other hand, it could be quite dangerous because now you're seeing local news to you, but you're missing out on, that's crowding out some other news, maybe news about Syria, maybe news about something that you should be reading or that might be diverse news, that might be from a different political perspective and so on. So we're going to have to grapple with the fact that aggregators are essential, they use machine learning, they're incredibly impactful, you're going to have a small number of them, and that's going to change who we are, what we know, and how our democracies work.
Okay, well with that, I think we're going to end our panel, but thank you all for joining us.
Yeah, thank you so much.